Good morning, everybody. How are you? Happy Sunday. I hope that you're doing well. I hope that your families are doing well. I hope that you're having a good day. I hope that it's not too hot where you live. I am doing great. It is beautiful, beautiful weather out today. I went out this morning at 4:30 to go walk my dog, take him to the dog park. And I was shocked at how cool it was. Like it was like I really debated wearing a jacket, which is crazy. And we're still in August. I live in the desert, but it was actually very nice, borderline cool out there. So I appreciate that the weather is changing. I appreciate that I get an opportunity to spend time with all of you. I think we're going to have a great stream today. We have chapter 8 of the Introduction to Statistical Learning book coming up. So I'm really excited. I know that you guys are excited. We've been getting some great attendance during these classes. So I'm really looking forward to spending this time with you today. I hope you packed a lunch. I hope you brought your thinking caps, because today's chapter, the level of difficulty goes up a little bit, right? But I know that many of you have been here since chapter 1. And I know that we've been learning, and just as always, I'm going to do my best to keep things simple, to keep things easy to understand, make it easy for everybody to understand. So I think we have a really interesting chapter ahead of us. I really enjoyed putting the materials together. There's a lot of messages I want to convey during this chapter. So I think we're gonna have a really good time with it. And by the way, today is the last of our 3 sessions. So we have today together, and then we have 2 more Sundays. And then that's it. We're done with the book. There's only 10 chapters to the book. So for those of you that have been here since chapter 1, you should feel good about the progress we've made. I'm really proud of all of us. And after today, there's only 2 more chapters. So that's incredible. All right. So I'm seeing some people already joining in, which is great. If this is your first time joining us, welcome. I'm getting a lot of new followers and subscribers. So, it's okay if it's your first time. We always start off by letting us know where you're from, so feel free to let us know your city, state, country, province, just to kind of build some fellowship in the chat and all that. But otherwise, the focus of today is going to be the class. It's going to be chapter 8. And just really, want to get started on it because I think it's going to be a lot of fun. So also in the chats on all the platforms, I have put a link to the Discord. Because if you want to have questions about the chapter, or you want to collaborate with someone, or you want to talk to more people away from the streams, like maybe you only watch the stream and replays or whatnot, go to our Discord, join our Discord. Lots of really good people there. Lots of really good discussion there. So please go ahead and join us. I offer it because I want the community to help each other. And then I also kind of give my opinion whenever needed or whatnot. So really looking forward to having you as part of that community there. Also on Instagram, just to make things a little bit easier to see, I have gone ahead and made it so that the widescreen view is available in the pinned comment. It might be easier for you to join us on YouTube, where you're going to see more information. You're going to see more of the slides and the code and whatnot. I think it's also a little bit easier to participate in the chat. So if you'd like to join us over on YouTube, that's also available, okay? But let's go ahead and start looking at the people that are in the chat. And then I just want to get started. I just want to go ahead and get to the materials. We're going to be doing a lot of interesting stuff today. Today we're going to be building upon a lot of what we've already learned. So it's going to be interesting. It's going to be super interesting. All right, so Rohan's reclaiming his place at the top. Good morning, Dennis. All Rohan from Vizag, India. Coming in first, Rohan. It's good to see you. I know you've been a great supporter, so thanks so much for being here. Hope you're getting a lot out of these classes. Casual Economist says, good morning. Hey, Casual Economist. I think yesterday was your first time ever attending, so glad to see that you're back. Today's a little bit of a different stream. It's going to be more of a class stream. This is the way that I do instructional content. I don't do pre-recorded instructional content. So today you're going to have the benefit of a class. We're going to do the Introduction to Statistical Learning Chapter 8. So glad you're here. Rex, how you doing? Good morning, everyone. This is Rex from New York City. Happy to be part of this awesome community. Thank you so much, Rex. And we're grateful you're part of it too. So Rex is in New York City, and he's also one of my moderators on Twitch. So he helps me, keep things calm over there. And he's actually also one of my moderators on Discord. So a shout out to Rex for helping out. Michael says, happy Sunday, Sir Dennis, and everyone. Happy Sunday to you too, Michael. Hope that you're doing well. I believe that you are in Nigeria, if I remember right. So hope you're doing well out there. Yassine, our man in Morocco, says, hello, sir. Yassine from Fez, Morocco. Well, good to see you, Yassine. Hope you're doing well. Okay, is that all the introductions we have today? Geez, I guess people are being shy, or maybe people are being a little slower to join this morning because it's a Sunday or whatnot. I know that August is a popular time for vacations, right? So it's not always easy to catch people on Sundays, but we've been having great turnouts and great participation. So I have no doubt that people are going to join us later. And I appreciate that you guys were early. So I'm tempted to go ahead and get started and just, people will come. But as always, I always will ask questions at the chat and people will join in as they can. Okay. Casual Economist says, I watched up to chapter 4 in the, wow. I watched up to chapter 4. That's a lot. That would be like at least 4 hours of content, maybe like even 4.5 hours. That's a lot. Wow. That's a big commitment, Casual Economist. Good for you. Good for you. I mean, right now, I think the entire collection is well over 12 hours. I think it's like 12.5. So yeah, I mean, up to chapter 4 is like almost 5 hours, like 4.5 hours, something like that. So good for you. Wow. Lakshmi, good morning, Lakshmi. Lakshmi says, morning, Dennis and all. Good to see you back, Lakshmi. Lakshmi's been a consistent attendee on Sundays for the classes, so I hope you're getting a lot out of them, Lakshmi. Okay, so last call for introductions, but otherwise, I'm going to go ahead and get started. We have quite a few slides to go through today, so I just want to go ahead and get started. You guys are early, so, I don't want to do all of you a disservice by not starting. Joseph says, morning, Dennis. Happy Sunday. Good morning to you too, Joseph. Joseph's one of our moderators on YouTube and also on Discord. So shout out to Joseph. Thanks for being here. All right. So I'm going to go ahead and jump in. So today, hey, Manoj. Manoj says, good morning, Dennis. Good to see you, Manoj. Glad you're here. So today we are going to talk about chapter 8. And chapter 8 in the book is known as tree-based methods. And I don't know if you got a chance to read ahead in the chapter or not, but from a visual perspective, tree-based methods are basically exactly like what they sound like, right? I'll show you a picture on the next slide. But let's establish kind of like why we're even doing this chapter. So to kind of set the tone, we know that a lot of our current study is focused on linear regression. And then we also know that we do not live in a world where things are linear, right? In the previous chapter, last week's chapter, it showed us how to work with data that's not linear, right? We have a variety of different plots, and we can try to find the best path through the plot, which is not always a line. And then we also learn about like polynomial regression, things along those lines, right? So the whole point of this chapter is to show you another way, an alternative way for us to work with data that is not linear. So in the last two chapters, we're accepting that the world is not linear. So in this chapter, we're learning a second set of tools to help us deal and work with data that is not linear. That's it. That's all we're doing, right? So try to not get caught up in the different definitions and even some of the math in this chapter. What is the tool that we're learning? And that's it, right? This is the tool we're learning. We're learning an alternative way for us to work with data that is not linear. And that makes sense because most problems that you're going to run into aren't necessarily linear. Okay? So, the underlying theory of trees, the tree methods overall, is that data can always be segmented. right? There's always ways for you to segment out your data. Whether you see it initially or not, right? A properly trained and executed model can find segments in data. And then you can use the attributes of those segments to allocate it to a new segment. And finally, the rules that are used for the allocation are easily displayed in a tree. And that's why it's called a tree-based method, or how the term trees or decision trees or things like that came to be. I also want you to note that in the first two bullets, I've put parentheses. That in the first one, it's data can always be broken out into segments. How you find those segments is basically the training cycle of your algorithm. The second bullet is you can then use the attributes of the new data to allocate it to a segment. And that's your prediction cycle. So those parentheses are my own. The authors don't lay it out that way. But I am taking this opportunity to be able to present it to you so that you can realize that, hey, when I'm working with algorithms overall, I need to distinguish between what I'm training and when I'm running new predictions. And this is your first view into that. Or this is one of the better ways for me to illustrate it. Creating the segments, creating the tree is like your training cycle. And then taking the new data and allocating it based on the attributes of that data is your prediction cycle. Super important to understand the distinction. And the reason I say that is because when you get out there, you're actually working on live models, working in a live environment. You're only going to be deploying the prediction side. You basically never have to deploy your training side. So I'm using this opportunity to kind of start making that division in your mind, because it's important the further you go, or the closer you get to approaching like your first professional job in data science. The authors don't really lay it out this way. Like nobody really laid it out this way for me until I was, pretty close to like being a data scientist already. So that's why I'm doing this now, because I think it's important. Okay? But overall, the 3 bullet points that you see on this slide are the essence of why trees exist. Trees help you segment your data and then helps you understand where new data should be allocated. So the authors also concede that tree-based methods have their downsides. They may not be as powerful as other approaches, but they also have their upsides, and we'll talk about those, right? So the chapter also includes bagging, random forest, and boosting. And we'll talk about those 3. But really, the overall goal here is just to understand the fundamental approach of trees. Because if you can do that, then the other 3, bagging, random forest, and boosting, will kind of fall into place for you. You'll see them as just different additional ways to create the same tree, like more refined ways to create the same tree. Okay? All right. So like, what is a tree, right? So this is a diagram that the authors put forward. So throughout this chapter, they are using a data set of baseball players. The baseball players, their personal statistics as far as how they're playing, and then their salary. Okay? So that's what you're seeing here. This is a tree that's trying to predict the salary that a particular player will make. So here, the first decision point is how many years they've been playing. If they've been playing for less than 4.5 years, 5.1 is about their salary. If they've been playing more than 4.5 years, you go to a second decision point, and then you figure out how many hits they have. And then based on the level of hits, you're determining their salary. So everything you see on here is a tree. Every time you see a split, that's referred to as a branch. And then everything else you see, as far as like the years, the value for the years, and the value for the salary, that's all determined by the model. The model essentially creates this tree for you. So as you can imagine, years and hits is an attribute in your data, right? Those are features in your data. And then salary is your target variable, right? That also exists in your data. So years, hits are your predictors, salary is your target, and these are all branches, and then the contents of those branches and how many branches you have, when you need the branches, that's all a function of the model and the math behind the model. But whenever you think of a tree-based approach, you should be thinking of something like this. And then the authors also have this additional chart over on the right-hand side. Remember how we talked about segmenting your data? So this is an example of that segmentation. So here it's telling you that this is your first segment, R1, this is your second segment, R2, and this is your third segment, R3. So if you remember, our first decision point was the years. So the years down here is 4.5, right? So that's why everything to the left of 4.5, in other words, 0 and 4.5, is in segment 1, right? To match this leaf, this branch over here. R2 says they're above 4.5, but they have less than 117 hits. So that's how you get the 6.0 branch. And then R3 says they have more than 4.5 years and they have above 117.5 hits. So that's how you get this branch over here into this salary level. So these segments are telling you about your data, and then they're also telling you about your target variable. That's how you're determining the target variable. So every tree that you do, you should be able to have a corresponding chart that looks very similar to this. Okay? Amrampali, good to see you. Hello, Dennis. Joined a bit late today. Well, I hope you brought a note from your parents, Amrampali. You can't be late to class. Parimal, good morning, sir. Good to see you, Parimal. Hope you're doing well. All right, so I hope that we're clear so far, right? We have 3 different branches at the end, and then we have 3 different segments on our chart. So, seems pretty clear, right? I think everything is pretty easy to kind of correlate between the 2 charts. But I want to spend a little bit more time on this chart. This chart is super interesting to me. And I'm going to challenge you guys a little bit. I'm going to challenge you guys to think about last week's class. Because last week we had a lot of really good discussion on the ridge regression, finding your path through your data, polynomial regression. We had a lot of really good stuff last week. For the moment, I want you to ignore the segments that the tree gave you. And I want you to just look at the dots. Let's just look at the scatter plot. Okay? What do you see in this scatter plot? If you were to tie last week's lesson to this week's lesson, what do you see in the scatter plot? I'm going to give you guys a minute or so to think about that. Feel free to talk it out. There's no wrong answers. But, you know, you guys should be able to start tying things together a little bit, right? And there's an opportunity here to do that. What do you guys see? Is anybody like, just like, is anybody moved by something in this chart? Wow, nobody? Are we all being shy this morning? Is nobody moved by the chart? Again, ignore the segments. Just look at the scatter plot. Anything jumping out? Okay, so Yassine says there are two features that can enable us to separate the data, and I think that years has more impact on our prediction. Not sure if I'm on board with that, Yassine. I'm not sure if I'm 100% on board with that. Manoj says data points align vertically. Yes, but that's only because years is how they measure it, right? Okay. Amram Pali. Amram Pali says looks very sparse to me. Okay. Yeah, Amram Pali says also vertical. Amram Pali, you had me at sparse, you lost me at vertical. So guys, it's only vertical because, you know, because it's a yearly measurement, right? It's not a very frequent measurement, so that's why it's you know, it's going to look very vertical, right? But let's focus on what Amram Pali first said. It looks very sparse to me. And she's right? That's what got me. That's what caught my eye, right? So again, let's think about last week, right? Can somebody point to the parabola in this? Can you please show me where the x cubed is? Or can you please show me where the quadratic x is? Remember how we did all those charts last week? Remember how we talked about how sometimes it just really kind of comes down to like pattern recognition, where you'll see the data and it's like, oh, gee, that data looks like a parabola. I should be using polynomial regression, right? Can you guys can you point to the parabola in this? Or remember how we talked that ridge regression is putting a path through your data? Can you imagine a ridge that goes through this data that wouldn't have a lot of errors? I mean, you could see the paths, but it'd be a lot of errors, right? Like there's no single path that really has that covers a lot, right? Because again, the data is very sparse, right? So Yassine says maybe that it's not a regression problem. Yep. Okay. So now we're on the right track. Yassine, I'm much more on board with this answer than the other answer. So if we combine Amram Pali's answer and Yassine's answer, now we're on the right track. So I'm using this to illustrate to you guys that last week we learned about polynomial regression and like the ridge regression and things like that, right? Remember these ridges, how we can have like these very like distinct breaks in the data in the data and in the paths? Those are all very strong methods, but they're not always gonna work. And in the reverse of that, just because you see sparse data doesn't mean that there isn't a model there. And that's really kind of what I'm trying to get across to you guys, right? Because just as we talked about pattern recognition, the parabolas, the x cubes and all that, I don't want you to look at a chart like this and say, there's no model there. There could be a model there, right? And maybe trees is it. As Yassine says, maybe it's just not a regression problem. Doesn't mean there's not a model there. It doesn't mean that there is a model there either. But the takeaway here is that this is why you have to try multiple models against the same data. You know, later on, we're going to talk about like the champion model process, right? Where that is necessary for you to do that. So yes, it's sparse data. So regression you might test and throw out, but hey, maybe trees is what you're supposed to be doing, right? You don't know. You don't know until you try. You can't just throw away this data and say, oh, there's no viable model there just because it looks sparse, or just because you can't see a line there or a regression line there, right? So I hope you guys are with me on that. This is a really important concept. It's really important for you guys to realize that just because it's sparse, just because one method that you tried, you know, didn't go well, doesn't mean that there's no model there or that you stop. You keep going. Maybe after today, the tree model, it won't be strong enough either. That's okay. You move on to that. Now you're trying a third model, and that's okay. You just keep going. Okay? So I hope that's clear. Let me know if you have any feedback on that in the chat. Super, super important concept, okay? Michael says a spline, I guess. Yeah, Michael, that's not incorrect, but it's really hard to imagine even a spline line that fits but doesn't have a lot of errors, right? Because I mean, look at this group of outliers out here. Look at this group of outliers out here. You have these over here that are not outliers because there's so many of them. Like, where is the path? Where is the line that isn't going to put you so far away from at least one, maybe all of those outliers, right? Like, it's too sparse for there to be a viable path here. So I like that you're, you know, trying to apply from last week, but I just don't see it, you know? It'd be really hard to find a spline of any kind, you know, even if it's a smooth spline that wouldn't have so many of these errors, right? Because remember, you're measuring the errors by the distance of the real truth to the line, right? So a lot of these would have really far distances to any reasonable line you could draw. Giovanni says, I was going by chapter 3 so far. Okay, Giovanni, well, thanks for joining us. Chapter 3 is the first lesson. So we've had an additional 4 lessons since then. So you got a lot of catching up to do, my friend, but thanks for joining. Rohit says, please center the screen. Rohit, if you can, I have pinned the YouTube link in the Instagram chat. So please visit us on YouTube. It's a little bit easier to see there, okay? Rohan says, so model selection is a try and check approach. Yes, absolutely. Absolutely, Rohan. Yeah. Yeah, so like if you're a member of our Discord, you might have seen where Yassine has posted some analysis that he did after one of our classes. where I think it was the housing data, and we were talking about regression then, right? And he posted where he could improve the baseline, metric by a little bit, but not a lot, and certainly not anything ready for modeling. So yeah, at that point you could say, okay, time to try another model, and you move on, right? You still want to carry over that metric, right? That's still a valid baseline model, but then you move on to the next model, a tree-based model or whatever, and you say, okay, well, can I beat that baseline metric, right? This would indicate you can, right? Because tree-based is like an inherently different approach, right? But yeah, you absolutely do that. You say, okay, this is I spent, a reasonable amount of time on regression methods. My, let's just say my R squared, let's say, was, 0.57, which is better than nothing, but it's not great. So let me carry over that 0.57. That's the mark I'm trying to beat. Let me try trees. Let me try neural networks. Let me try something else, right? So yeah, you got it right, Rohan. That's what you do. Rohan says, so it takes time and practice to try which model works best for the given problem. Yes, you are trying to find the model that works best for the given problem, but I wouldn't say it's time and practice, to be frankly honest with you. It's two things. One, you have to have knowledge of a decent number of models, right? You can only try what you know, so you have to educate yourself to make sure you know how to using those models properly, right? And that's what we're doing, and we're going to talk about that a little bit later, by the way. But that's what we're doing, right? You're building up your toolbox of models, right? So you have to know a decent amount of models. And then two, honestly, it's just discipline. It's just discipline. A lot of individual data scientists and even a lot of teams get lazy on how they go about running this process, right? And if you remember in my live streams, I always ask that trick question, right? What's your favorite machine learning model, right? You shouldn't have a favorite machine learning model, right? That type of weakness affects this process, Rohan. Because now you're always going to say, oh, well, I know neural networks really well, so I'm going to try neural networks, right? That's going to be like your go-to model, right? Your favorite model. And that's bad. You shouldn't do that, right? So it's more about, so you have the right concept, Rohan, but it's not just time and practice. It's the knowledge of models and the discipline to do it. And then just so you guys know, just to kind of put some scale around all of this, I'm not going to lie, we didn't do this every single time because of time constraints or other factors. But if you work for me, I want to see you try at least 8 to 10 different models on data. If we're working on a new problem, new project, we're trying to stand up and you're trying to propose a solution to me, I want to see your documentation, or I want you to talk to me about trying 8 to 10 models on the same data. Another piece of scale is when I did my graduate studies, I had a capstone course that, went through a full model. And in that course, we were required to try 13 different models. So, just to kind of give you guys scale of what that looks like in the real world, right? So like a graduate course is going to ask you, for like at least a dozen models. And then if you work for somebody like me, I'm going to ask you for 8 to 10 models against the same data. So it's really just a discipline to enforce that and the knowledge to be able to do that. Like do you literally know how to use 10 models in a sound way? Like have you put in the hours studying that? Okay. Great question, Rohan. Thank you. All right, guys. So let's keep moving forward. The authors, I'm about to give you guys a super important point here, okay? And this point is so important that I often have the same conversation with some of my corporate clients, okay? So the authors have this really interesting paragraph in this chapter. And I have, the highlights are my own. The highlights are not from the author. Those are my own. And I have highlighted how they have listed out the regions, right? they have listed out the regions and they have an explanation, and then they have like a mathematical or, formulaic representation of the region. I want you guys to think about this, because this also speaks to implementation. Doesn't this look like something you could implement in code? Doesn't this look like something you could implement like in a business rules engine? Right? Like, there's plenty of business rule engines out there that'll help you with this. I mean, heck, if you really wanted to get creative with it, you could probably implement this in Excel, right? You could program a macro or some VBA or whatever to, run this, right? Or, pick your favorite business rules engine, come up with a new group of rules. These are your rules, and you implement it wherever you need to implement it, right? So I'm putting emphasis on this point because I want you guys to realize, again, super important, not every implementation you do is programmatic or going to be like some heavy implementation, like like a deployment, like a massive deployment of some kind. Okay, some implementations you can do like this. You can do it in a business rules engine. You could do this in Excel. So remember how we talked about training cycles and prediction cycles? This could be your prediction cycle in Excel. You could program a macro that does this, right? So I'm saying this because I want you guys to realize that when you're talking about, I work for a company that uses algorithms, or I work for a company that makes data-driven decisions, it can be business rules. It's just that those business rules were created by an algorithm, right? The implementation is a business rules engine, but the parameters and the factors, the features in those business rules have been algorithmically determined. That's super important. A lot of people don't get this. I remember, I'll tell you a story. I remember that I was working for a large company, and I was working in a separate department from one of the directors that I had become friends with. I was working in the Dallas office. They were in the London office. He was a director, tons of experience, really smart guy, not a technical guy, but he knew data and he led data science teams. And that's how we got to know each other, and he respected my opinion. He would send me papers that maybe I shouldn't say this, but he would send me stuff that his team wrote for him, his team of data scientists wrote for him, that he wanted me to double check and advise him on. Maybe I shouldn't have said that, but like I was his person to help him verify the stuff, right? And one day he called me and we had a long conversation about this, where I had to walk him through, because his team proposed a business rule solution, right? And I had to walk him through how that was a valid solution, because you're still using an algorithm to determine what the rule is, but your implementation of those rules can be anything you want. I mean, this could be a simple Python script too, right? I didn't mention that earlier, but it could be a simple Python script. It doesn't even have to call any saved libraries or any trained model or anything like that. It could literally be just like a filter you write in Python. That's a perfectly valid implementation for models like these tree-based methods. You'll have to update it, and maybe it adds just a little bit more to your maintenance overhead, but there's no reason why you can't say, here's the results of the model, go to a business rule engine, and these are the rules I want you to write for that engine, and we will be making data-driven decisions. Okay? So if I've lost you a little bit, that's okay. You'll understand more as you get into actually deploying models and actually putting your work out there. But I'm using this to emphasize that not every deployment is this big, involved, big reveal type of massive deployment. It can be as simple as saying, hey, we did the modeling. We know that this is a good business rules engine that's going to get you to where you want. So we're going to go ahead and propose this and say, and your deliverable is a document that has the rules that team goes and implements. And how they implement it, may or may not be of interest to you. But you're still providing algorithmic results, even though it's a set of rules, right? So super important, guys. Okay, I hope you find that helpful. So Rohan says thank you. Amram Pali says different cases we implement as to take decisions. Yeah, that's right, Amram Pali. But my emphasis is on how you implement those, right? And the implementations can be a lot easier than most people realize. Okay. Sammy says, on my level, a model, for example, is just classifier equals random forest classifier. So what's hard about implementing many models? Sammy, not really sure where you're going with that. Sorry, Sammy, give me some more information in the chat. Not really sure what to do with that one, okay? Rahul says hi, Dennis. Hey, Rahul, nice to see you. Hope you're well. All right, let's move on to the next slide. I think we've gotten enough out of this slide. So, you should also realize that there's essentially no limit to the number of branches your tree can have. And we saw that in other models, right? Like if you remember our conversation about regression, you can have, those breaks, those splines, you can have as many breaks as you want, the knots, right? They're referred to as knots. There's no limit to the number of knots you can have, right? But, well, excuse me. So with no limit to branches, no limit to these knots, you can do a process known as tree pruning. And tree pruning is where you start with a very large tree and then you find a subtree. You find a more effective subtree. Because the challenge is that with tree pruning, it can also be a very, without tree pruning, if you have these large trees, it can also be a very small model to run, right? That model all of a sudden becomes really, really big to run. Because you have so many branches going out, right? There's a lot of decision points. The more decision points, the more processing power that is required, right? But there's another problem here. Does anybody see it? Does anybody see the problem? So aside from processing power, what is another problem here? You can have unlimited branches, which is similar to the number of knots that you can have in regression. There's no limit to the number of knots. So we know that would add to our processing power. But what else is a problem here? What was the problem with knots? If you guys remember from last week. I'll give you guys a minute to think about that. So Yassine says overfitting. Any other answers out there? Michael says overfitting. Rahul says, I think this too. Okay. Yep. I mean, you guys are right. Overfitting is a massive problem there, right? It's a big risk when you do that. Because technically you could have a branch for every single possible result, right? Like there's basically nothing stopping you from doing that. You could have as many final results, final segments as you wanted to, right? So yeah, that's the danger, that you're going to have overfitting. And that's where you're going to be doing some cross-validation to help you with that. Because cross-validation, it's what's used to prune that tree and to come up with the best possible results while still having the minimal number of branches. So cross-validation is going to help you find the balance between a model that's overfit, i.e. too many branches, versus one that has the least possible number of branches with the most accuracy. Okay? So essentially, the authors take the time to show you what the initial model looked like. This is what they initially started with, okay? And the model that they show later, I think, do I have it on? I do not have it. Is what you end up with after pruning. So this will give you an idea of what they start off with, right? So here you can see they have 1, 2, 3, 4, 5, 7, 9, 10, 11, 12 different branches in their initial tree. But if you measure by the MSE and, you know, use a solid cross-validation process, you can prune this down quite a bit. And that's what they're showing on the next chart. Sagoon says overfitting. Yep. Building subtrees may be an unnecessary avenue. Why do you say that, Tim? Let us know your rationale in the chat. So on this chart, you're able to see the cross-validation portions, right? And then you're also able to see what your training and your test data give you. And you can see how they came up with the final number of 3 branches. Because that's basically this dot right here. At 3 branches, you got the lowest MSE. The more branches you add, the higher the MSE goes. And that makes sense, right? Because we just said that the more branches you have, the more overfit your model becomes. And you can see that here in the training data, right? The training data loves more branches, right? Because your MSE just keeps dropping. But that's also an overfit model because your cross-validation went up, right? So this is an example of what the pruning does, and honestly, an example of what some of the other models we're going to see today do too. So we're determining that the right answer is 3 branches. And then this same process helps you understand which of the 3 branches to use. So spend some time with this chart in the book because it's super key. But again, put it all together. We just agreed that more branches is an overfit model. And we see that in the black line, right? The black line is characteristic of an overfit model. The green line is what you're really interested in, right? The unseen data, how the model performs against the completely unseen data, right? So that's what you want to optimize for, and the optimal number, according to this chart, is 3. Okay. All right. And that's how you ended up with this, right? That's how we come back to the initial chart of 3 branches, and then it helps you determine which are the best 3 branches. It could be any of the branches, right? Any combination of the 3 branches. But the model also helps you find which 3 branches. Because each combination of 3 branches is going to have its own MSE, right? So the model is telling us that these 3 branches represent the lowest MSE of all the possible 3 combinations. All right. All right, so let's take a little bit of a pause here. And, I want to hear back from you guys, all right? Now that we've learned a bit about trees, Feel free to answer either one or both of these and answer as many times as you want. But what do you think are the benefits of trees? And do you see any downsides to trees? What are the benefits and what are the downsides of trees? I'll give you guys a minute to think about that. Oh, and by the way, I should have mentioned that this is an interview question that I ask. One of my interview questions is, what is a decision tree, and are there any limits to a decision tree? I think is what I ask. Or what is a downside of decision trees? I asked something like that in my interviews. So this is an important question, guys. Yassine says it helps when problems are not linear and likely not a regression problem. You're not wrong, but you can say this for every non-regression model, couldn't you? Like, couldn't you have given the same answer if we were looking at neural networks today? Right? So you're not wrong, but that's not specific to trees. Random Seed 42 says working on nonlinear data. Yeah, but any model that's nonlinear, you could say the same thing about, right? Oluwesegun, I don't think I've seen you before. If it's your first time, welcome. Trees provide an easy way to find relationships between input and target features. Okay. Okay. All right. I can be sold on that. You know, don't misunderstand me. We've gotten some good answers so far, but what else? I mean, what is unique to trees that stands out to you? Maybe we'll take more computation time and might capture more noise sometimes from the data. Kind of the overfit thing. Okay, Amrampali. Okay. You're hitting on a couple interesting things, right? Where you might, yeah, I mean, depending on the size of your segments, you could be missing a lot. You could be introducing a lot of noise into the results. I get that. Olaweskin says, my first time. Oh, well, welcome. Glad you're here. If you're a little lost or want to get caught up on the other classes, feel free to look in my archives. I have all my classes up there. And then I'm also playing them on a loop. So sometimes you'll see me live, but I'm playing the loop of all the classes. So feel free to look at those. Downsides, I think that it's very sensitive to outliers. Yeah, absolutely, Yassine. There you go. It is sensitive to outliers. Because again, just like I said, right, depending on your segments, that segment may still have a lot of different scatter plots in between, right? So, data points in between. So yeah. Ah, Michael, love the answer, my friend. They look easy to understand and interpret. That's that's super key, Michael. Super key. Why? Because it's easy to explain to your business stakeholders, right? How many times, guys? How many times have I told you guys? 1, you will be judged on your business impact. Nobody cares about the math or code you wrote. It's about the business impact. And 2, don't talk to your stakeholders like a math guy or a code guy, right? I always tell you guys that, right? You guys know this. Decision trees are an excellent way to do that, right? So Michael's hitting on a super key point. Decision trees are easy to interpret and they're easy to explain to business people. So that's a huge upside for decision trees. So Michael, good answer. Yassine says it can create segments. Yep. Yeah, but a lot of models can do that though, Yassine, right? That's not unique here. Regression can create segments, right? It's a categorization. Categorization and segments is the same word, right? Manoa says use when we are interested in multiple class. Yeah, but regression can do that too, right? Rahul says it can be used in downside overfitting advantages, less data preparation. I'm going to come back to that, Rahul. I'm going to come back to your point. Okay. Oluwasegun says trees do not necessarily require normalization or too much data pre-processing. Yeah, you're basically saying the same thing as Rahul, and I'm going to come back to that. Nithin says downside of overfitting. Potential overfitting. In the next couple of slides, we're going to see how you can avoid overfitting. And remember, overfitting is not unique to this model. Overfitting can be done in every model. It's just a different way, right? Rahul says easy splitting. Yeah. Abhishek says, which chapter is it going on? Abhishek, we're on chapter 8 of the Introduction to Statistical Learning book. I see that you're on Instagram. On Instagram, you're going to find the link to the YouTube feed, which is a little easier to see because it's widescreen, so feel free to switch over, Abhishek. Okay, so I want to come back to the comments that Rahul Oluwasegun made about the less data preparation and too much data pre-processing, right? I think those are really important points, guys. And I would tell you that that's actually a downside to trees. I say again, that is a downside to decision trees. Okay? Here's why. I want you to think of a model. Well, the model that we've been looking at, right? And really everything we've been looking at, we've been looking at like sales, we looked at like the TV advertising versus sales. We're looking at the baseball players, years versus salary, right? Those are fairly straightforward data sets. But what about when we start to get to data sets that have like a ton of inputs, right? Like for example, NLP, right? In NLP, every word is an input, right? The tokens. Or what about computer vision, where every pixel and the attributes of that pixel is an input, right? That's how at a fundamental level, that's how computer vision works, right? It takes an image, breaks out the pixels, and gets the attributes and so on, right? So you could be talking about models that literally have like hundreds, thousands, multiple thousands of inputs. Do you think a decision tree would perform well? Give me a 1. Give me a 1 in the chat if you think a decision tree would perform well like that, or give me a 0 if you don't think it would perform well. Like knowing what we know now and seeing the branches and the examples we have, do you really want to use this model for like 5,000 inputs? Like, does that make sense to use this model for that? Give me a 1 if you would do that, a 0 if you wouldn't do that. Oluwasegun says, what if we limit the application to tabular data? 2 things. 1, that's not always your decision. That's not your decision to make. That's the stakeholder decision to make. And 2, even tabular data can be pretty big, right? There's plenty of situations where you would have tables with like, a couple hundred inputs easily, right? So give me a 1 in the chat if you would use decision trees with a lot of inputs, and give me a 0 if you wouldn't use it. All right, couple of votes coming in. Don't be shy. You can just vote. Nobody's going to call on you. Any other votes? Lakshmi says, which with large data, it can be computationally expensive. Yeah, okay. Most people are voting 0. And so you guys got it, right? Decision trees don't do well with large number of inputs. That's the model. I bring that up because that's the model answer I look for when I ask this question. Because I told you guys I asked this question, what's the downside? And that's one of them, right? I mean, right now, everybody on this chat or in my live streams has asked me about LLMs and Gen AI. Those are approaches or problems that require like tens of thousands of inputs. So think about the branches that you would create if you were to do this with the decision tree. It's just not practical. I mean, at the top level, right? Every single one of your pixels would be like an input, right? Or each one of your words or whatever would be like an input. So Lakshmi, I don't disagree with you that it's computationally expensive, but that is the what do they say? That's the result, not the cause, right? The cause is that decision trees are just not good for a lot of inputs, right? So that's what would cause, the massive number of branches, and obviously it takes up the processing time from there, right? But the cause is that decision trees are kind of like pigeonholed into really only working with particular data sets, right? Like you wouldn't present like a computer vision answer with decision trees. It's just it's from a design perspective, it's just not practical. Michael says it looks less suited for complex relationships. Yeah, Michael, I'd agree with that. Rahul says, so less data preparation is a downside. No, Rahul, it's more that it's less data preparation because you're using less inputs, you're using less features. But I'm referring to how it's that number of features, that lower number of inputs that is more appropriate for decision trees, which is also a weakness, right? Like, for example, a large number of computer vision models don't really require a lot of pre-processing. So it fits your criteria, right? That it's low pre-processing, but who cares? There's still too many inputs for decision trees to handle, right? I mean, even a small image is 128 by 128, right? So what's 128 times 128? That's the number of pixels. That's the number of your inputs, right? Doesn't matter whether you have to pre-process them or not. That's a lot of inputs. So that's really more about what I mean by that, okay? Rahul says, what is the data have less inputs, so can't be advantage? I don't know what you mean by that, Rahul. Can you suggest what type of data is best? Maybe a limit to the number of input features? I don't think there's any hard or fast rule here, Oluwagesan, but, most business problems, like smaller business problems, are gonna fit this model, right? Like when somebody talks to you about like budgets or about financial projections, something where you're gonna have a moderate number of inputs, I think is where, you're gonna find that a decision tree is a little bit more manageable to do, okay? Nithin says, higher the number of inputs, I think ANN works better. No, I don't agree with that. You can't say that. You can't say that. That's a fallacy of logic, right? You can't say because X doesn't work, it means that Y must work. You can't say that. The only thing you know is that X doesn't work, right? You can't just jump to another solution. You can jump away from that and say, maybe I shouldn't try decision trees here, but that shouldn't change your champion model search. You should just be able to put decision trees to the side, but you still keep an open field to all the other models you're going to try. You know, coming back to our previous discussion, maybe you have a result with regression that's not great. You have your R-squared value, your baseline that you're holding. You try trees, and trees doesn't improve on that baseline. That's okay, right? You still ran valid experiments. It's just that your baseline wasn't beaten. But that doesn't immediately say, oh, A and N must be the answer. It just means you need to move on. So be careful with that, Nathan. It's a logic gap that you're exhibiting there. So be careful with that. You got to keep an open mind to what the answer can be. All right. Rahul says, I got it. Thanks. Okay, Rahul. Okay. So just so you guys know, I encourage you to read the text. These are the items that the authors present as what they see as the upsides and downsides. So some of these you guys already hit upon, right? They're easy to explain. They mirror human decisions. You can easily display them graphically, and you can handle qualitative variables without having to create dummy variables, right? Because they also talk about qualitative factors. So, you know, Michael's answer, was a great answer because it basically kind of hits upon all of these, right? And then they also see the downside, right? They're not as predictive as some of the other models, and they are sensitive to changes in the data. They are sensitive to how you create the trees, right? And we're going to see some of that because some of the next items is basically an improvement upon trees, right? So we're going to see this here. So let's talk about bagging. Bagging is our next approach for trees. So trees can suffer from high variance from the training data, right? Because as some of you correctly identified, right? Even though you're creating these segments, there's still a lot of noise there, right? So even just a small change in where you go from those segments, right? Kind of moves the needle on some of these other scatter plots, right? What if you were to go from 4.5 years to 5 years? Just that little half value change introduces a lot of noise, or removes and introduces noise, right? So if you guys remember our old friend bootstrapping is going to help you with that. What bootstrapping does, if you remember from our previous chapter, I believe it was chapter 5, maybe? Can't remember. We talked about how sometimes you might have limited data, right? So it's going to require you to resample the same data over and over again. And you might have instances where you're using the same piece of data twice in your training set, and that's okay. That's part of the bootstrapping effort, right? So in bagging is essentially bootstrapping for trees. You're going to sample the data over and over again. And instead of taking one tree, and by looking at multiple trees, you're able to take some of that variance out of it. Because now you're kind of able to converge on a tree that more likely represents the consensus of your data, because you've done it multiple times with multiple trees instead of one tree. Because you can always find, the optimal tree, but that's not to say that there aren't other trees out there. So when you hear bagging, you should hear bootstrapping. And when you hear bootstrapping, you should hear resampling. You're just resampling your data over and over again to help you come up with the best model possible. So Yassine, this should resonate with you because you mentioned this in your write-up about, the housing data, right? about how you pick the different features can also affect your model, right? We talked about this with like subset selections, right? And like the I think the lasso approach. How you pick those features, like literally the order of how you have those features, affects your model. So it's kind of like the same thing here. So that's really all you need to know. You know, we're about to learn a couple of different terms that sound intimidating, that sound complicated, but they're really just variations on the same theme as they relate to trees. So let's move on. Random forests. What is random forest? Random forest, bagging is good, but bagging resamples and creates those random collections of your data. Random forest is a random collection of your features. Okay? Subtle but important difference there. The random collection of your data helps you find a better model. But you can improve on that by also saying, well, I also want a random collection of my features. And that's what random forest helps you with. All right. Nathan says, does resampling cause duplicates in the data sets? Yes, that may be a result of bootstrapping. I hesitated to say that there because we shouldn't view it as a byproduct or a risk of bootstrapping. The whole point of bootstrapping is to do that, right? Like you shouldn't be resistant to it. That's the whole point of bootstrapping. That you can kind of like, you know, artificially create your data sets, but it's still valid data. It's just used multiple times. So it's a valid approach. Has its downsides, of course, but it is a valid approach. But yes, bootstrapping does cause duplicates in your data. Yes. Random forests. Excuse me, sorry, I don't want to tie those two. I just want to tie bagging and random forest together. So bagging, random collection of data, random forest, random collection of features. And just as before, now you're not just doing one tree, you're doing a variety of trees. And this time, the trees aren't necessarily related. Because this tree over here has different features, this tree has different features. Same MSE, right? Same MSE, but can have completely different features. Because again, we just said that trees have a lot of noise, kind of susceptible to that, right? So you can have two trees, completely different features, very similar MSE, very similar performance, right? But a random forest method can help you find the optimal tree. So let's keep going down here. So here's what you're looking at. This is a pretty good chart that they display for the random forest. Up in the upper right hand corner here, you should know that P stands for the number of predictors that are used. M is the number of predictors that are used for this particular random forest run. So you're going to have M is half of the number of predictors, and M is the square root of the number of predictors. I don't know if they have like any logic on why they chose these. You can certainly just choose them at random, right? It almost kind of doesn't matter. What matters is that you try as many permutations as you can of half the predictors, of all the predictors, of the square root of predictors. So really, I think that these values, I hope I'm not wrong on this, but I think that these values in the upper right-hand corner can be anything you want. They just can't be greater than P, right? Because P is your entire feature set. But then these are your results here. It's not just the number of feature, but it's also the number of trees, right? This is the number of trees that they tried. And then over here, this is your MSE on your test data. I don't know why they didn't show cross-validation error. But here you can see that M equals P, the square root of P, at 100 trees or maybe 90 trees is going to give you your lowest classification error. So this is how you're combining all of those concepts to say, okay, I'm going to use all of my features. I'm going to try different collections of those features. I'm going to try all the permutations within those collections, and I'm going to see what happens. So a little bit of a brute force approach, right? Because you're basically saying any feature in any combination of features can be the answer. Just try everything. But it's a valid approach, right? It's like a Monte Carlo-esque approach. But this is chart 8.10 if you want to look it up. But this should help you kind of put everything together in that regard. Yassine says, can you please talk more about how random forest collects random features? Is it just like subset selection for tree-based math? It is. It is, Yassine. So if you guys remember, Yassine here is referring to subset selection. And we saw that in the previous chapter when we talked about feature selection for regression methods. And in that one, subset selection, you're basically saying, okay, my model could have two relevant features or two independent variables, right? So give me all permutation of two variables and try it. Okay, what about three variables? Give me all permutations of three variables and try it. And so on and so on and so on. And you can do that basically for however many number of features are in your data set. So yes, Yassine, it's the same thing here. The only difference here, Yassine, is that you're saying how many features you want to try. So that's, again, upper right-hand corner, that's the M value. In your orange line, you're saying try every feature. In your, what is this, in your blue line, you're saying try half of all the features. And in your green line, you're saying just try the square root of all the features. Right, because down here, it explains how P equals 500 predictors. So yes, Yassine, it's very similar to that in the sense that you're giving some general parameters, and then the model just runs all the permutations, right? Which is exactly subset selection. So I love that you made that tie together. You're on the right track. Okay. All right. So finally, I think this is the last one we're learning. But we're going to talk about boosting. So boosting and bagging are kind of like kissing cousins, right? So with bagging, you're taking your random samples of your data, but everything is created, every model, each iteration is like a separate test. Like it just tests it and throws it away, tests it and throws it away. But in boosting, you're saying, okay, I ran that test. What did I learn from that? Okay, maybe I can improve on that. Okay, I improved on that, but there's another part, maybe I can improve on that, and then improve on that, and then improve on that, right? So that's what boosting does, and that's what I'm saying here in the last slide, right? Boosting will create a fairly large model to start, and then it'll say, well, you know what? This branch over here doesn't quite look right. Can I optimize this branch? And it'll go off and it'll just fix that branch, right? It'll do other iterations just for that branch. Other bagging type iterations, by the way. And then it'll say, okay, yep, improve that. And then it comes over here. Oh, okay. Yeah, this branch could also use improvement. And then it'll run like a boosting type process, a bagging type process on just that branch. And it'll refine that base model. So that's boosting, right? That it doesn't just say, oh, I ran this random iteration. I got an okay result, but I'm throwing away the model. All right, so bagging and boosting are similar, But bagging just uses models once. Bagging tries to improve the models. Excuse me, I said that wrong. Bagging just once. Boosting tries to improve the model. It builds on what it's learned. It tries to improve the individual branches. All right. Oliver Gesson says, I would like to ask what software tool you use for this brute force approach, because I'm not sure libraries like sklearn have this. They absolutely have this. They absolutely have this. It's just happening underneath the hood. Right? I mean, I'm presenting you the theory, but how we're going to implement it is obviously via libraries, right? And more importantly, we're going to do it via AI, right? So one of our first questions is going to be, how do you, how can I do this, right? Because remember, we're not going to be code writers, we're code editors. And we do that by using AI as our employee. Okay? Yassine says, thank you, sir. You're welcome, Yassine. Hope that's making sense. If it's not Yassine, please let me know in the chart or catch me on Discord later. I know that you're, a really serious student of this, so love to help you out. Just let me know. Nithin says, what MSE are you going to define which permutation is better? There is nothing, right? I mean, MSE is a relative term. MSE is relative to other MSEs. There is no single threshold per se. It's just what is your best MSE out of all your possible, all your available MSEs from all your other models. So there is no threshold. It just is what it is, right? I mean, that's part of the testing. All right, so let's look what's next. Yes, so boosting also gives you some tuning parameters. Now remember that tuning parameters are important because tuning parameters do what? Tuning parameters drive our testing, right? You can't test if there's nothing else to try, right? So tuning parameters are good because it gives us different tests to try, different values to try. So in boosting, you can choose a number of trees to use overall. You can also use lambda, which acts as a learning rate for the model. If you remember, we've seen lambda before, right? Lambda is almost kind of like a speed dial, right? It's like a speed dial for how things degrade or how things learn. So lambda is back. And then we have this other value of D, which represents the number of splits in a tree. Now, I put an asterisk next to this one because, I don't want to mislead you guys, mislead all of you or give you guys bad information. But I'm not sure I fully understood what D does. So I invite you to read the book on boosting. I kind of understood it, and this was my interpretation of it, that it's the number of splits. But I'm open to being wrong on that. So if one of you wants to take that on and, come back to me with a better answer, please let me know. But again, I don't want to lie to you and tell you I fully understood it. I want to be honest with you guys. So I'm not sure I fully understood it. So if you guys want to, find something else for it, please do so. But that's what I understood it to be, that it's a number of splits in a tree. Regardless, the bottom line is that we now have 3 different hyperparameters that we could be trying. So that kind of gives you the scope of the number of tests that we can also run, right? Because now we have we have permutations of 3 different values that we could try, which is good, right? You want to have, as I tell all the data scientists that work for me, you want to have levers to pull, right? You always want to have something to try, right? Your model doesn't suck until you run out of things to try. You can still improve it, right? There's still opportunity for you to improve it. Oluwa Second says, how can I use AI for this? Do you have a video on this? Yeah, you're about to see it. You're about to see it, or you can look at my previous classes where where we all use ChatGPT for this. Okay, so hang out, just calm down. All right. So where are we next? That might be it. Okay, yeah. So that's it for this chapter. Okay. But I thought that this is a really good opportunity for all of us to kind of take a step back and really just kind of see what we've learned, right? So just kind of taking a meta view of everything that we've covered. I want you guys to realize that all of you should have some knowledge on all of the models that are up on the screen, right? We've gone over linear regression, logistic regression, polynomials. We Yassine earlier mentioned subsets. We've done the lasso. Today we talked about decision trees, about bagging, random forest, boosting. We've covered a lot, right? And I want you to kind of think about this in this way also, because as you've heard me say before, these are all just tools, right? You're just adding to your toolbox, right? That's all we're doing here. We're just adding to our toolbox. We're mechanics buying nice new wrenches, but we still have to educate ourselves on how to use them, when to use them, what the results mean, so on and so forth, right? That's the methodology of data science. But I personally am in awe. I'm standing in awe of this list because all of you who have attended, or if you watch the replays, we've covered all of these. And this is how you progress in your career. This is how you get closer to becoming an actual data scientist, of landing a job in the field, because this is what the start of a professional toolbox looks like. Right? So I thought that this was an appropriate time for us to just kind of step back and think about everything that we've covered. You guys should be proud of yourselves because we really have done quite a bit. All of you should be able to speak at least a little bit to all of these models. We're 8/10 through the book, right? So these are all tools that you can use in the future to help you with this type of stuff. Right? You should know how to use all of these. So good job, everybody. I think this is great. We're going to keep on adding to this, right? We still got 2 more chapters after today. But lots of progress, lots of good advancement. Okay? All right, so I think we're ready to go for the coding portion. Yeah. All right, so I know we have some new people, so let me cover the framework again. What is the result that we are optimizing for, right? We have to have something to test against, something that creates our champion model, our baseline to measure against. We are going to be level 2 data scientists. We're going to be using an LLM for assistance. And we are going to be code editors, not code writers. We're never starting from a blank screen. Okay? We are going to establish a professional level development environment. We do not work in notebooks. We're going to find an appropriate data set. And then we're going to try 2 pieces of code. We're going to use a decision tree and we're going to use a random forest. All right. And then we're going to output some plots as needed. All right. So let's go ahead and get started. I just realized that I don't have my visual code and all that ready to go as I usually do. So let me get my act together here, guys. It's gonna take me a little bit. Wow, I definitely do not have my act together. I haven't even got my folders done. Oh, you guys. All right, so this is ISLA 6. And this is our code from last week. Oh, guys, I've been so busy. I didn't even get everything ready. Actually, let me rename. All right, so that's ISLA 6. We're going to create a new file in here, and we're going to call this decision tree, because that's the first model we're going to work on. And now I got to prepare my terminal window. So give me a second on that, guys. Okay, there's my terminal. Need to make that bigger. I think that's pretty good for you guys. And then I need to activate my environment. Okay, there's my file, decisiontree.py, okay? All right, so that's it, right? That's all we're writing. Remember, we are code editors, not code writers. Starting with a blank screen is for the dinosaurs. And we're not going to be doing that, all right? Yeah, all right, so let's bring up our good friend ChatGPT. So we're going to find out what ChatGPT knows. I'm pretty sure sklearn is part of it, but we'll see. I think it was Oluwasegun that asked that earlier, right? So there you go, Oluwasegun. It says that scikit-learn has it. XGBoost we could also be using. LightGBM and CatBoost. Let's see if it suggests anything else. Oh, TensorFlow also has it. So plenty of frameworks for us to use. We've been using scikit-learn, so I want to stick with that because I think scikit-learn, just writes us a little bit cleaner code, right? So let's go ahead and use that and say, we got to find some data, right? Scikit-learn does not include the baseball salary set. However, you can easily obtain this from various online sources. Loading from a local file. Okay, so it does not have that data set. That's okay. Maybe scikit-learn has something else we can use. Actually, maybe we can use the housing data set, huh? I'm just not sure that had enough features for us, but let's see. The iris dataset. The wine dataset. 108 samples with 13 features. That might be good. The breast cancer dataset. 30 features, 569 samples. That's pretty good too. Diabetes dataset. I think that's also known as the Pima Indians dataset, I remember. Okay, so the Boston housing dataset we know we've tried to use. Yeah, California is more for regression, which makes sense. I don't think it'd be good for that. Okay, you know what? Let's use the wine dataset. So if you're not familiar with the wine dataset, it tries to classify wines based on the attributes that are contained within the records for the wine. It's a very common data set to use in academic classes. So, it doesn't hurt to be familiar with that data set. Okay, so yeah, the target variable representing the type of line, 3 different classes. All right, I think we should use that. I think that'll provide us some pretty straightforward examples for us to think about. Because really what we're going to try here is we're going to try a decision tree, just a plain vanilla decision tree. And then we're going to try a random forest. And let's see what the different answers are, different quality of results we can get, okay? All right. Let's see what the results are here. Okay, so one thing, well, let me bring this code over to Visual Studio so you guys can see it a little bit better. So just from my quick read, the code seems very reasonable, right? We're loading the wine data set. We're splitting our train test data. We're declaring that we want to use a basic decision tree classifier. It's going to set a random seed for us. It's going to go ahead and fit it. It's going to run your predictions against your test data. And then in this case, guys, this is a little bit different, just slightly different. We are going to, it's a classification problem, right? So classification problems are best displayed with confusion matrices. So in this case, the measurement that it's using is the accuracy level, right? And that's okay. That's a totally valid metric. So up to this point, we've been talking about MSE, but in this scenario, it's actually going to use the accuracy as the metric that we're measuring against. So our question is always, here's the accuracy of our baseline model. Can we improve upon that accuracy, right? So slightly different than what we've been talking about before, but still a completely valid approach, okay? So I think that this code seems fairly reasonable. It's only 37 lines of code, and it wrote it to us in less than 5 minutes, guys. We got to this code in less than 5 minutes. That's pretty darn good. All right, so I think that we should execute this because really it's not very complex. I mean, these 3 lines is the heart of it, right? We're declaring the decision tree classifier as our desired model. We're asking it to fit the model. And then we're asking it to run the predictions. And then based on those predictions is where you're getting the accuracy scores, right? So fairly straightforward. For those of you that have been attending every class, this is your 6th class, this should look fairly standard to you too. But let's try it, right? You never know until you run it. So okay, wow. The accuracy is 0.94. That is not bad. You can see here in our classification report that we have 3 different classes, right? The accuracy across all classes is 0.94. And the F1 scores are perfectly reasonable. Because remember, F1 scores are a combination of your precision and your recall, right? So all of these look fairly reasonable to me. Remember, however, that the support column is also the number of members of that class. So in other words, there were 14 members in class 0, 14 members in class 1, and 8 members in class 2. So this isn't a very deep data set, unfortunately. And maybe, maybe we'll switch to a deeper data set, right? I don't know. Maybe it was a mistake to choose this. We'll find out. But this is what we're getting with a plain vanilla decision tree. And then down here is our confusion matrix. The confusion matrix isn't very well done. I don't think we should be happy with that metric. So let's ask ChatGPT to change it. We're not going to change it. ChatGPT is going to change it, okay? Oh, wow. It even ran the code for us in the example. I didn't even see that. Wow. Did you guys see that? Wow, look at that. We literally generated the same table. That's crazy. That's crazy. So ChatGPT is not only writing the code for you, it also outputs the results for you. So you don't even need an IDE, right? Like it'll run it for you. It'll say, yeah, here's the code. I know you like it. Let me just go ahead and run it for you. That's crazy, guys. That is cool. I haven't seen that before. And somebody can correct me in the chat if I'm wrong, but in our previous classes, I don't think I've seen it do that either. I don't think I've seen it where it'll just say, oh yeah, let me just run the code for you. That's crazy. All right, so let's see what it gives us here. Okay, wow. So it's actually going to plot it for us, which is great. And it gave the example, but it didn't show the plot as an example, which is interesting. That's interesting that it's willing to show us this, but not the plot. Okay. Maybe that's a limitation. All right, so let's run this. And we're going to see a plot pop up when this code finishes. Oh, it needs Seaborn. Okay, that's fine. Should work now. Okay. So here it opened it up in a different window. So you can see down here, we got the same results in the confusion matrix, right? Accuracy 0.94, same layout. But now we're getting a visual result to the confusion matrix. Really, this looks really good. Essentially, the model only made 2 errors, right? That's what we're saying. We're saying that this up here was misclassified and that this up here was misclassified. Everything else was perfectly classified in the model. Now keep in mind though, the entire data set is 36, right? So the classification, well, I shouldn't say that. The entire data set is, our validation set is only 36 members, right? So is that enough to say that this is a great working model? No, you probably want more members in your validation class. But still, for those of you wondering, this is what a very encouraging confusion matrix looks like. So we're going to move on to doing the the random forest approach, but I'm not optimistic that we can classify, that we can improve on this, right? All right, so somebody write that down. The accuracy is 0.94, and that's our baseline. That's what we want to improve upon, right? So let's try it. Let's try something else. We go back to ChatGPT and we get it to work. So one of the things I like to do is I kind of like to bookmark the latest code, right? So I'm going to ask it to do that, right? Okay, so now we bookmarked it for us to use in the future. So now, well, I want to make sure I also say I want to use the same metrics. All right, let's see what it does. Oh man, look at that. I love this. This is beautiful. This is beautiful. All right. Let me bring this up and we're going to need a new file. This is going to be random forest.py. All right. So here's why I love this, guys. Well, you tell me. Let's get the chat going again. Why do I love this? Sorry, let me bring that up again. Sorry. I think that this is beautiful, right? Why am I in awe of this code? Why am I in awe of what we just did? Anything catching somebody's eye here? I think the code is correct, by the way. But I think this is just beautiful. Why is that? What do you guys see? Hey, Stefan, welcome to the chat. Stefan, I see that you're on Instagram. It might be easier for you to switch over to YouTube to see the wider screen. The link to the YouTube is a pinned comment in Instagram if you want to look at that, okay? So guys, I'm going to look at some of these questions. You know, think about that. Why should we be in awe of this code right now? Michael says, and also step functions. Yeah, Michael, you're right. I might have forgotten to include step functions in my previous list, but you're right. Step functions is another one. Good eye, Michael. See, that means you're on top of things. I like that. Good job. Sarp says, will you go into mathematical statistics or high dimensional or dependent statistics, or how you use any of these? Not just today, but I'm wondering if you'll ever discuss these topics. Sarp, I don't think I've seen you before. If it's your first time, welcome. Sarp, so my goal is to demonstrate and to create content that shows real-world data science of how it's done. So real-world data science and the math behind it is using libraries. So yes, we are using some of these methods that you mentioned, but we're doing it all under the hood, right? If you want to work in the field, you know, in a corporate environment or, you know, as a data scientist, it's probably more critical for you to learn how to execute these models, how to be creative with models, how to create business impact with the models, than it is to get too caught up in the individual intricacies of statistics or of math or algorithmic mathematics, right? So that's not really what I teach. I just don't think it's practical. I think it's overrated. I teach more about how we can actually use the models and be functional with them, okay? Yassine says clarified steps. But it was clear before, right? It was clear over here too, right? They did the same, they had the same steps too, right, Yassine? So what else? Oluwasegun says properly commented. Yeah, but but so was this. This is a decision tree code, right? I mean, that was properly commented too, yeah? What else, guys? Anybody else? All right. You're getting closer, Yassine. Use the same testing size and the same approach used previously. It did use the same approach in the data, yes. So you're very close, Yassine. What I'm in awe of is it's just one line difference, guys. But look at these two. Line 17 is really the only one that changed. And even then, only this declaration changed. To be more specific, right? So I wanna leave you guys with, I want to impress that in your minds, because when we talk about testing and trying different models and you know, knowing when to move on from your baseline, it's not complex, guys. The code does not always have to be complex. And this is why we use libraries, right? Because libraries can make it easy to switch from one to the other. So I'm really enjoying how right here before our very eyes, we have two completely separate tests. We have two legitimate tests that we are running on completely different models, different approaches, different math, right? We have people asking about math. But it's literally just one, not even a whole line, one declaration within that line. That's all it takes to try a completely different test, a completely different algorithmic approach. So I want to impress that upon you, because this is where I get disappointed when teams lose that discipline to try, well, teams and individuals lose that discipline to try different models, to run an appropriate champion model search. In a lot of cases, it's just like this. It's just one line of difference. Just try something else. Try a variation on your code. And ChatGPT kind of makes it easy, right? Because on ChatGPT, you can say, okay, cool, I like that model. I like those outputs. I like everything you did there. But now just do it with another model, and then a different model, and so on, right? But I really want you guys to take this to heart, because this is how simple trying different models can be, okay? So I think I've hit on that point enough, but you guys know that I'm big on methodology. I'm big on people executing data science properly. And a lot of teams go wrong right here, where they jump to neural networks, they jump to their favorite model, they jump to something else. But just try it, just execute the code, try it. You don't know until you try, okay? Oluwasegun asking a great question here. Do you recommend hyperparameter optimization before switching to another model? Yes. Yes, Oluwasegun. You want to get the most you can out of that one model approach. So yes, you would want to try to get the most you can out of decision trees and then move on. Get the most you can out of random forest and then move on, right? You definitely want that, yes. Having said that, it doesn't always have to be in sequence. You can run some of these things in parallel, right? Like we could set up the model in the hyperparameter tuning and then run it overnight, right? Like all three, like let's say we're trying both of these that we're looking at. And then you want to compare your best hyperparameter tuned model to or decision trees to your best hyperparameter tuned model for random forest. So yeah, you absolutely want to make sure you're getting the most out of it. And before you make the decision to say, okay, I'm going to put this model to the side. So yeah, great question. But yeah, you definitely want to do that. You want to maximize what you can out of those models. Okay. All right. So let's run this. We haven't run this. What's our baseline again? Somebody remind me in the chat. I think I called it, well, what did I call this? I think I called it random forest or forests. Random forest. Wow. Tell me what you see. Tell me in the chat. What do you guys see? Yeah, thank you, I guess, and it was 0.94. Thank you for that. Thank you, Rahul. All right, what do you guys see now? Please interpret the chart that is on the screen. I like Lakshmi's assessment of improved. Yeah, we've improved. Anybody else? You can look, if you're shy, you're just hanging back, that's okay. You can just choose to agree with a person. Maybe you just want to agree with Yassine, or you just want to agree with Lakshmi. That's totally okay. But I know we have more people watching than participating, so feel free to just say, yes, I agree with Lakshmi, or I agree with Yassine. Rahul says 100, yep. I get it, Lakshmi. I'm just having fun with your answer, but I get it. Michael says too sweet. Let me know what you mean by that, Michael. All right. Well, yeah. I mean, you guys are catching it, right? We're perfect, right? We're perfect on the accuracy, which is great, right? Now, two things here, guys, right? To be practical about this. One, this example is serving my previous notion to you guys that random forest should give you a better result, right? Trees is like just a basic, plain vanilla decision tree, right? It's a single model. It doesn't take very long to compute. It's pretty straightforward. Whereas random forest is a lot more complex. It's trying random features. It's trying all combinations of things, so on and so forth, right? So it met our goal in the sense that we show that they're an improvement, because there should be an improvement, right? A random forest is a much more complex approach, so there should be a significant. You should be disappointed, or maybe even suspicious of the quality of your code if there was no improvement, right? Now, that doesn't mean you're always going to reach one, but there should be some rise above whatever your baseline is. It just so happens our baseline was very high in this scenario. So for that goal, I hope that this is illustrated to you about how much more better or improved results you can get with random forest over a decision tree, right? From a practical perspective, you should always be suspicious of models get a 1.0. In this case, though, there's only 36 in the cross-validation. So, you know, I'm okay with it being 1.0, right? That's going to happen on such a low sample size. But again, the purpose of understanding that a decision tree is going to be very, very hard to perform better than a random forest because of the same theories that we just learned about, right? I hope that makes sense to you guys, okay? Yassine says, can you please give your opinion? But whenever I see 100% accuracy, I get the sense that something isn't right, like overfitting or not enough data. Rahul says, yeah. Would I be able to rely on a model with 100% accuracy? Agree with Yassine? Yeah, but I just explained it to you guys, right? I mean, what's throwing us off here is the 36 sample, right? In cross-validation. That's a very, very small set. So yeah, you are going to get 1.0s in that scenario. So I'm going to ask you to put that to the side in your mind. The takeaway here from a lesson perspective is that we got the expected result in the sense that we significantly improved over your standard plain decision tree model, right? Yes, you should be suspicious of 1.0 results, but I would be even more suspicious if one of my employees came to me and says, I got this with the decision tree and I got a lower result with random forest. That should be a rare occurrence, right? And again, this model, it just so happens we had a very high baseline with the plain decision tree. Okay, so I hope you guys are able to make that distinction, right? Let's put the 1.0 to the side. You know, that was kind of an anomaly because, you know, such a small cross-validation set. But the win is seeing the improvement, okay? So, to help illustrate that, let's do the same exercises with different data sets this time, okay? We're gonna ask for a better data set this time. So let's ask ChatGPT. And let's go ahead and bookmark this also, right? All right, so now let's ask for a better data set. All right, let's see what ChatGPT says. Titanic is 891 rows. That might be good. Adult census income set. Okay, that's 48,000 rows, 14 features. California housing set. Kaggle data. Okay, so it's pulling from other data sets. Adult census income. It's trying to predict individual income exceeds 50,000 a year. Okay, so that's, in other words, that's a binary decision problem. And Titanic is also binary because it's a survival of a Titanic. But this one has 48,000 rows. Okay, I like this one. And it comes from sklearn. So let's try it. We're going to repeat the same exercises, guys, but with these deeper data sets. So we're going to see that same improvement or that same result. It just won't be 1.0 because I think some of you are being thrown off by the 1.0. So let's do that. Adult census income data set. Okay. Oh my gosh, that's still going? Come on. That's enough. Stop. Wow, that's a long answer it's giving. It's giving every single result. Jeez. Please show me tree 1 with the adult income data set instead. All right. Okay, so this is going to be a little bit more complex because 1, it's going to be a binary model, guys. And 2, you can see it's doing some pre-processing, right? Like it's handling missing values. So this is good. It'll be good for us to see this. So we need a new file again. Decision tree v2. Let's see what this gives us. We're not gonna be too fussy about the code because we know that we're still using this same line, right? The decision tree classifier. That's no surprise. We saw that earlier. It's just using a different data set and different pre-processing, right? That's it. Again, we're just doing this to better illustrate the difference between a standard decision tree and a random forest. So we'll run through this pretty quickly. So decision tree v2, and this might take a little longer to process. Oh, wow. What is it telling us? It's some sort of error in one of the columns, right? Could not convert string to float and self-employment not included. Okay, is that one of the ones that the code pre-processed? I don't think it is. Huh. That's weird. How is ChatGPT giving us an answer when the code wouldn't run? Let's copy this and tell ChatGPT. All right, so ChatGPT is claiming to have fixed itself, which is still weird that it gave us an answer, right? Maybe the answer is a hallucination. But then again, we're about to verify that if we're going to run the code ourselves, right? Same error. That's weird. Oh, wait. Cursor change from auto. You can set, therefore, and pandas is not installed. Okay, maybe it's my own local install. So the way we can fix that is we can ask ChatGPT what pip installs I need. Maybe I just don't have the right installs. Pretty sure I already have all. I'd be surprised if I don't have pandas. Yeah, which I already have. I forgot what the pip install to force an upgrade is, so we'll ask. Okay, so it's an upgrade. Just to make sure I'm not, you know, doing something locally bad. No, that's already done. Let me close this out. That's a little. That's already also satisfied. That's weird. It can't be Seaborn. We just installed that. And the last one is matplotlib. Weird. Okay, so it's already satisfied. Everything's updated. So what's going on here, guys? Anybody spotting something that I'm doing that's just clearly wrong? What do you guys think? The Valley's trying to be sending a copy size. See the caveats. I'm gonna ask ChatGPT one more time about this. Okay, so it's gonna try to do it one more time. Oh. Maybe I didn't save the code. Oh man, that might have been my fault. Maybe I didn't save before running. Shoot. That would have caused the same error, wouldn't it? That might have been my fault, guys. Nope. Huh. I think somebody had a suggestion in the chat. Rahul says, I faced the same error, faced the same problem before, couldn't resolve it then. Although Augustin says you could try checking the label encoder method. You could try ordinal encoder. This is why I love live streaming, because it teaches how you professionals go out solving problems that rise in the real world. Well, Rex, I'm tempted to solve this by just dropping the column. I don't know how great that is. Let's just do that. Let's just drop the column. You don't want to do that in an actual setting, but just to kind of get us beyond this, I want to do that. All right. So we copied that over. And we're going to do that. Oh, you got to be kidding me. How is that still? That is super weird, guys. No rule. I faced the same problem before, couldn't resolve it then. Okay, so maybe this is a known issue, guys. Why didn't you guys tell me before choosing this data set? Come on, guys. All right. Let's do something else. Real quick, let's switch over. We're just going to switch over to the Titanic dataset. It's the same thing, right? It's a binary selection. Maybe not as many records in it, but still a valid approach to do what we want to do. Because again, I'm not trying to show you guys data. I'm trying to show you guys the difference between the results of the decision tree versus random forest. Okay. So that's done. Oh, I copied it too early. I got too anxious. I copied it too early. There we go. That'll learn me. Okay, this is not great, guys. This is not good. You can set parser equals auto to silence this warning. But this is not a warning though. The first part's a warning, but down here, this is a value error. Huh. Where would we even set that parser equals auto though? I'm guessing that it's in the fetch. Yeah. What if we set? Let's follow what it actually says in the error, but I'm not optimistic that this is going to help us too much. We're probably still going to get the error, yeah. Yeah, so we got rid of the warning, but not the error. Because the error is still male appearing in what it thinks should be a float, what it should be a float column. Man, that's annoying. I don't think we can drop the categorical features like we tried before, because the Titanic dataset, if I remember right, is heavy on categorical features, right? Like your gender and other things. So I don't think we can do that. Shank says, are you in a virtual environment? Yes, I am, of course. I think the problem appears when the algorithm tries to deal with non-numeric values as the error appears in the fit method. Yeah, you're right. I guess the error is due to the data type not converted when we use the encoder. Maybe. I just checked. Actually, the model can't handle categorical data. Try changing label encoder to ordinal encoder. Yeah, you think so? It doesn't like that so far. Well, I guess we'd have to do it up here too, right? All right, let's try Oluwagesen's suggestion. Okay, didn't like that, but different error. Expected a 2D array, got a 1D array instead. Huh. Let's go back to ChatGPT. Properly encoding the categorical features to handle missing values. Okay, well, that would help. Age, fair, embarked. Okay, so it's doing a little bit more with the variables. All right, let's try this. What a mystery, hey chat. But it looks like some of you have come across this before. Still didn't like it. So we know that it's most likely a gender column, right? Let's see if we can ask it to focus on that. Okay, so there's a sex column that it needs to revisit. I didn't see it make a change though. Where is it addressing the sex column? Does anybody see it? I don't see it. I see code that is literally the exact same as before. That is weird, guys. I'm not happy with how ChatGPT is trying to fix this. Chat, what do you guys think? Maybe, maybe try Google Gemini. Wow. Not a lot of faith in ChatGPT, huh? Have we label encoder transformed? Yeah, we have. That's down here, right? What if we were to drop sex here? Let's add that to our list. I think that's going to greatly affect our results. Wow. It's having problems across the board. So this is a whole separate different column that it's having problems with. So it just doesn't like the categorical columns at all. Weird, right, guys? That is weird. Can you try to open a new tab of ChatGPT and ask it to correct the error? Maybe the amount of context is causing it to get confused. You know, Yassine, that's a really interesting suggestion. The problem I have with that suggestion though, Yassine, is that all of the LLM companies, right, the AI companies, they always say that context is one of their biggest like features, right? Like, you know, if you remember like Google Gemini, right? They announced that their context goes like some ridiculous amount, like a terabyte of context or something. Like, to these LLMs, more context, more better, right? So that's the problem I'm having with your suggestion, that it just doesn't make sense, right? Like, a lot of these companies are saying, hey, you know, context is the thing. That's kind of like what they're competing on, right? All right, well, I guess wants me to scroll down. This code is the same, all the way guessing, right? This is the same. It's really all in the data prep. But let me know if you see something. Meanwhile, we're gonna try Yassine's suggestion. I'm not enthused about it because yeah. Let me. So what do you think, Yassine? Give it back the code and say it's causing an error? Oh, whoops. So let's tell it what error it is. I want to go back. Where am I? I want to go back to this. I want to remove this. And then I want to get the error and feed it back. Please run the updated version of your code. Okay. I don't know what it updated. It doesn't look overly updated. Let's try running this. Oh, same error. Let me go back to the chat. Restart terminal. But when they say they can handle up to a certain amount of context, wouldn't that mean if we surpass the amount of the model, we'll start to make mistakes? Yeah, but we haven't done that, right? I mean, 2 terabytes of text is a lot of text, right? Like we would have to be like writing a lot to do that. Because that's the way I had it in my mind. Maybe I was really mistaken. No, I think you have the right instincts, but the limits for context is much higher than what most people think, right? I mean, 2 terabytes of just your text is like an encyclopedia's worth of text, right? Like a whole series. It's not a book. It's a series of books, right? So yeah, it's just I don't think that's it. Yeah, class is a category variable, but it thinks that it should be a float. The model thinks it should be a float. So let's see what ChatGPT says if we just report back the same error. Might have some columns still being treated as strings. Handle potential mixed data types, which is good, right? Because we might have mixed data types. All right, this is doing a lot more pre-processing. All right, let's try this, guys. Oh, we got there, guys. We got there. Whew. We got there. I have got the error and it generally occurs with encoding the categorical data. Yeah, Rahul, that's what it was, right? The categorical variables were not being encoded properly. Maybe give us the code in Discord. She'll learn something trying to solve it from the error. I still think, but we solved it, Yassine. We solved it, man. Were you losing faith that we were going to do this? Come on. All right. So all of that just to get this. Yassine says hallelujah. Yeah, man. We got there. We got there. Yeah, why is the chat quiet now? Like nobody's cheering for this? Come on, guys. We did it. We did it. All right. So what do you guys see? We see a confusion matrix and then we see the visual confusion matrix and we see the accuracy. What do you guys think? Tell me, give me feedback. What do you guys think? So again, if you're not familiar with Titanic, it basically has the attributes of the passengers and whether they survived or not. What do you guys think? What do you think of the model? Yeah, so now we can leave the debugging behind and let's get back to the model. What do you guys think? Look at all the emojis coming in the chat. Yeah, we did it, guys. So what do you guys think about the model? Yassine says model is actually bad. Not terrible though. Not too terrible. Anybody else? Michael says not looking good. Guys, not every model is like 95 plus, right? All of a second says this model's a little bit above average. Yeah, above average. I mean, I really don't think it's all that bad. So one thing is jumping out at me. If we look in the graphic, isolate for the survived category. Yeah, that's right. That's right, Yassine. It's making a lot of errors here, right? In this line in particular, it's making a lot of errors in the survived, right? It's pretty good at telling you who didn't survive. Right? I mean that accuracy is actually higher than 65, right? It's the F1 score there is 73, right? So that's pretty good. In the did survive, it's not great, right? That accuracy, that F1 score is only 0.5. Right? So it's almost like a toss-up whether it's going to get it right or not. So that's not good, right? So yeah, but it's just a baseline, right? It's just a baseline for us to use, right? So we can improve, right? The whole point is to test, right? We ran a test. We have a baseline. Let's improve on the baseline. And this time, we're going to make it super easy on ourselves. Over here. And we're going to call a new, we're going to need a new file. And this is going to be random forest v2. And guess what, guys? Watch me closely. That's it, right? That's all we should have to change. We saw that in the earlier example, right? It literally just comes down to not even this one line, but this one declaration in the line. Where was it? Right here, right? That's all we got to change. That's how easy it can be, right? Let me make sure I got that right. I think I did. Oh, is it ensemble? Oh, I see. I pulled from the wrong one. I need to pull from ensemble. Yeah, there we go. But that's it. Just changing those two lines, the import and the actual declaration. We should be done after that, right? So let's go back. Python. Random forest v2.py. Oh. Okay. So random forest, it has a whole other set of its own problems. That's weird. Does not accept missing values encoded as NaN natively. Okay. All right. Well, maybe I got too ambitious. All right. Maybe it's going to change the pre-processing here. We'll see. Excuse me, guys. All right, let's copy this code. Let's carry this over. Let's see if we can run this. Yeah, it does not like that at all, does it? Guys, we went from one error to another error. Missing values, not properly. Here's how you can do it. Updated code with NaN handling. Okay. All right. So it looks like it's handling the missing values in a different way. We'll see whether that's true or not. Nope, same error. All right, ChatGPT, let's see if you can correct yourself one more time. What do you think, chat? Has anybody seen this error before? Yeah, you're right, Yassine. We haven't even talked about hyperparameter tuning, right? Right now, let's just get the initial models working. Man, that's the same error. Wow, look at that. Sex and embarked have quite a few NaN values. That's crazy. I think I saw a comment in the chat. Shakib, I don't think I've seen you before, so welcome. Dropping the NaN values will help. Yeah, you're right. And we know what they are, right? Sex and embarked. Why are there so many? That's crazy. All right, so we're going to take Shakib's suggestion here. All right, let's see what this does. All right, so it says it drops any rows of the remaining NaN values. Now, keep in mind though, right, this might have an effect on our results. However, since we're using random forest over a baseline of standard decision trees, we should still expect a net improvement. All right. So there should be no more of those values. Oh, same thing. Now we're back to those encoding problems. Oh. Well, that's annoying. Okay, looks like it's gonna drop and then encode? Is that the difference? Yeah, because here it's encoding and then dropping. So it's fixing itself to do the drop and then encode. That doesn't sound like a terrible idea. What do you guys think? So maybe ChatGPT was able to recognize that. But we'll see if it works first. Nope. What if we were to drop those columns entirely? Because we know what's causing it, right? We know that sex and embarked is causing it. It did not like dropping embarked. All right. Or did I misspell that? No, that's... All right, let's see how ChatGPT corrects itself. Okay, a lot more pre-processing code in this version. Wow, that's a lot of code actually. I'm curious. We're going to go from 79 lines to how many? To 92 lines. Yeah, it felt like a lot of code. Man, that's still the same error. What do you guys think? What's chat have to say about this? Shakib says encoding the category about... Yeah, but it's already doing that, Shakib. Right? There's clearly already code for it, right? So let's help GPT here. So it looks like hopefully it'll add handling specifically for that error. Yeah, there we go. So it is adding that. Okay. It's explicitly addressing that one column. My fear here is that it'll just point to another column that also needs help. Yeah, same thing. The problem is we can't easily figure out what column that is. Is it in the error somewhere? Does anybody see what column that is? I don't think it's going to be explicitly labeled out here. But I have a feeling it's the embarked column. Because we saw that embarked was also weird, right? It's our only other categorical column, so we can add that code ourselves, I think. Oh, wow. Oh, now we've gone full circle, guys. This is the same first error that we got. Oh no. Oh wow, we've gone full circle. Maybe the same suggestion from before, changing to ordinal encoder. Yeah, you guys think so? All right, I'm open to that. Yeah. We're talking about here, right? It still doesn't like the. Yeah, but how can it contain those values when we know there's none, right? Missing values after dropping those is like 0. It's 0 across the board. That is super weird, guys. Let's try ChatGPT one more time. Drop all NaN values before splitting the dataset. Oh. Okay, maybe. You'll have a lot of code. Convert string to float, Q. That is weird. One more time here. Okay, so it correctly identified that it's the embarked column. So is it gonna? Okay, so now it's okay. Look at that. It's adding new handling for the embarked column specifically. Okay. That makes me optimistic, right? Yeah, so it's handling the sex column explicitly, and it's handling the embarked column explicitly. All right, we got there, chat. Good job, ChatGPT. Woo, that was a big diversion just to show random forest, guys. Well, now that's creepy, the embark column. I don't know what's creepy about it. I mean, it's pretty normal. It just had it just needed explicit encoding, that's all. What do you guys think? What do you see? Tell me what you see. By the way, guys, we're coming up on 3 hours for this stream. About 2 hours of those were caused by ChatGPT errors. I shouldn't say that, by encoding errors. And by the way, guys, while you're thinking about that answer, you know what's really cool is if you look at the error that we gave ChatGPT, we just told it convert string to float Q. Now, I guessed that it was embarked because it's the only other categorical column. But if you look at ChatGPT's answer, it knew it because of the values that are contained in the embarked column. So it was smart enough to be able to say, okay, well, where is Q? Oh, that's the embarked column. And this is how I'm going to fix the embark column. I mean, come on, guys. If you're not impressed by that, I don't know what to tell you. That's pretty impressive that it was able to do that. I'm impressed by that. All right, so what do you guys think about the results? Oh, whoops. Sorry, I meant to bring that up. Wait, where am I? Yeah, terminal and then the graph. What do you guys think? I see improvements. Anyway, improved. What do you mean, Lakshmi? Michael says improved. Yeah. Yeah. You guys are right. Should we be surprised by that? No, right? We're supposed to get improvements, right? Sorry. We're supposed to get improvements. Random forest is an inherently different, arguably better approach, right? So what I'm liking is how we improved the survived column, right? Because what was our F1 score? Like 50.0.50, right? That's not a great F1 score. But now we're at 0.73, right? And for the not survived column, we're still at a really good F1 score. We improved the F1 score, right? Now we're at 0.85. That's great, right? So yeah, I hope that you understand. You know, if you put aside all the debugging we had to go through, I hope you understand how powerful random forest can be over decision trees, right? What the benefits are of experimentation. You should always be trying other models. You never know what's going to improve it. And then to Yassine's earlier point, we haven't even done any fine tuning, any hyperparameters, right? We still have some of those levers to pull, right? Lots of stuff that we could still be doing to help us. But yeah, but now we're on a better path, right? Now we're at a 0.80 overall accuracy. We've improved over the baseline model, right? Over the decision tree model. So now what do? Now we take this 0.80, that's our new champion model. But now we move forward and we try to beat it. Maybe neural networks will do better, right? Maybe other things will do better. And you move on and you try other things, right? So this is the power of experimentation and the power of trying different models. All right. Manoj says yes. Rahul says not surprised. Yep. Lakshmi says means after all the efforts of debugging got good results. Yeah. Unfortunately, though, Lakshmi, we weren't debugging the model. We were debugging the data. So, like, yeah, it's good, but it's not so good. But you know what? Like I said, in this final step, we should all be impressed that ChatGPT didn't give it the column, right? But ChatGPT took that Q value and said, oh, that most likely belongs to the embark column. And here's how I can how I can explicitly encode the embark column. Guys, that's pretty impressive. I mean, seriously. I mean, if you're not impressed by that, I don't know what to tell you. I think that's pretty cool. I think that's pretty cool. Wow, we are at the 3-hour mark. I am so proud of all of you for sticking through to the end. Thank you for hanging in there with me. I'm exhausted, and you guys are probably exhausted too. I gotta go get more water. I'm gonna go enjoy the rest of my day, but my day has been off to a great start because I've been able to spend it with you. If you want to carry this conversation over, feel free to join our Discord. Lots of really good people there. You know, feel free to come and talk to us. But otherwise, I hope you enjoy the rest of your day. I hope you've enjoyed this session. What a session, 3 hours, guys. So I'll see you again soon. Shakib, yes, I live stream every day at 1500 GMT, and this particular class is every Sunday at 1500 GMT. Rahul says we are the champs. Yeah, we should be proud of ourselves for getting this far. You're right, Rahul. We did great. We all did great. And some of you have been here all 3 hours. Gosh, good job, guys. And by the way, guys, I'm really proud of you guys because remember, this is 8 sessions, 10 chapters. We have done 8 of 10 chapters. Like this is a serious book, and we've done it. Like we only have 2 more to go. Good job, guys. Good job. Really proud of all of you, and thanks for hanging in there. So until next time, take care of yourselves, take care of your families, take care of the loved ones around you, and I'll see you next time.